All right, so 2.8 inverse functions. So an inverse function undoes what was applied to the input value of another function. Okay, let's try to break this down. So if you, let's look at the what I have here in green. So you have the function 2x minus 3. And the inverse function is this red line right here, okay? And that's the function x plus 3 divided by 2. So if you compare them, they just undo what the other one did. So the original green function, you're multiplying x by 2, and over here you're dividing by 2. The original function we have minus 3, and then the inverse function we have a plus 3. Okay, so you can sometimes visually tell when functions are inverses of each other, and we'll take a closer look at all that in a moment. But basically, let's look at this. So if you look at this green one here, let's see, I'm going to pick up this point right here. It looks like this point is like 2, 1, right? So when x equals 2, y equals 1, right? And so what will happen, the inverse function will just go in reverse. So you'll see when x is 1, y is 2. So let's color code this. So if you look right here, when x is 1, y is 2. And so you can see that the x and y basically switch roles. So you can see when I plug in 2, I get 1. And then if I plug in 1 to the inverse function, it sends me right back to 2. Okay, so if you look at the picture right here, you can see it's kind of like a loop. And so you plug in a value into the original function, and you get the return value. And then if you were to plug that value that you just obtained into the inverse function, that's inverse notation right there. We'll talk about that in just a second. That's the notation for inverse. You plug that value into your inverse function, it will send you directly back to where you started. So it's just kind of like a loop. And so if you look right here, just real quick, the function notation. So the notation is f inverse right here. So it's not like it's not an exponent. It's just a notation. Just means inverse function of f. Okay, and so it just kind of talks about that. It does not mean to take the reciprocal. You don't want to do that. You don't want to do that. It's just a notation. So here's one more example. So see, if you plug in 5 into the original function right here. So if you do 5 times 2 is 10. 10 minus 3 is 7. So it takes you to a 7 over here. Now, if you take 7 and plug that into the inverse function up here, you'll have 7 plus 3 is 10. 10 divided by 2, it takes you right back to a 5 right there. One other thing to look at, and you can see this on the graph of f inverse is a reflection of the graph of f across the line y equals x. So you see this dashed line y equals x. Inverse functions are a mirror image across this this dashed line right here. Okay. An inverse function maps the output value of a function back into the input value of the original function. The table of an inverse function will have the x and y values interchanged from the original function. Okay, so this is a lot. You know, we've been looking at this for about 4 minutes, and so it's a lot to digest. And so what we'll do is we're going to kind of take this a piece by piece. So right now I gave you the big picture. This was a lot of information. But now what we'll do is we'll look at little chunks of information. So the first thing we're going to look at is how can I verify two functions are inverses of each other? So if I'm given two functions, how can I figure out if they're inverses? Well, since the inverse of a function takes you back to where you started, the following holds. If the f of x and g of x are inverses of each other, then if you do a composite function where you stuff one into the other, it should return you to the original value right there, x. And it doesn't matter which one's stuffed into the other one. So you can stuff g of x into f or f of x into g. Either way, if it comes back as x, then that is, it has that relationship. And so, see, what's happening is going back up to this picture up here, right here. So see, you plug in x and it maps you to, you know, some new value over here, and that's what this would become inside the parentheses, and that value gets plugged back in and it will map you right back to where you started at x right there. So that's why if it results in x, they are inverse functions, because you're starting with x right here. You're starting, that's the first value that's plugged in, and that's where you return after you substitute it into g of x. Then that result gets substituted into f. And once that takes you back to there, then you've verified it. So let's go ahead and try this. So it doesn't matter which one I stuff in. So I'm going to do f of g of x. So see, I'm starting at x, and I'm going to see if it will end up with x. And so g of x, I'm going to go ahead and substitute that for this, right? G of x is equivalent to x minus 8 over 3. And so now I'm going to stuff that into the g function, I'm sorry, the f function right here. So this will become 3 times x minus 8 over 3, and then a plus 8 off to the side right there, right? Okay, so when I start to simplify this, you'll see that the 3's cancel out, and that'll leave me with x minus 8, and then I still have the plus 8. And the 8's are going to cancel out, and that will leave me with just an x right there. And so I verified that when I stuff one into the other, it simplifies into x. So basically, I started when I substituted x in, it mapped me over to this right here, whatever that is, right? And then it mapped me right back there when I substituted it into the f function. So this was g of x, and then this was f of x right there. I substituted it into those two functions, and it led me right back to where I started. Okay, now let's look at the part B. So we'll do the same thing here. So let's see, we'll do f of g of x. And so we're going to stuff this in there. So f of x plus 5 over 9. And we're going to go ahead and put that right there. So we're going to have 5 times x plus 5 over 9. And then we have a minus 9 right there. Okay. Well, unlike the last problem, these don't cancel out. I could go ahead and distribute this if I want. And so let's see, I'll get 5x plus 25 over 9 minus 9. And we could play around with this. We could get a common denominator. I'll go ahead and do that, but it's not going to work out here. So let's see. If I got a common denominator, this would become 5x plus 25 over 9. And then this will become minus 81 over 9. And if I subtract that 81 from the 25, I pretty much will get stuck after that point. So there's not really much I can do. So first problem, yes, they were inverses. Second problem, I couldn't simplify it down to x. So the answer is no, I could. They are not inverses of each other. Okay, so let's see. Let's go ahead and look at another aspect of these. So do all functions have inverse functions? Okay, do all functions have inverse functions? Okay, from previous knowledge, we know that a function is a relationship in which the input x results in a unique output y. Now, as seen before, the x's and y's trade places. So basically, your x and y will now become y and then x for your inverse function. They just switch places to create the inverse function. Therefore, for every y, there must only be one unique x for a function to have an inverse function. When a function has this trait, it is known as a one-to-one function. Basically, the way you can think about this is that each partner is faithful in a one-to-one function. So you got to remember back from our very first unit when we talked about what's a function. And basically, the only qualification was that X could only have one partner. Y could have multiple partners. That didn't really matter. It was just more important that X couldn't have more than one partner. And you might remember the vertical line test, right? And so this would pass a vertical line test right here. This one would not, because when X equals 2, I'm getting two different results, and that's a problem. It's not known as being functional. Because functions, you typically plug in your X value to get a data result. And if you're getting two different results, the function, it's not a function, it's broken, because you're getting two different results. Now, plugging in two different values and getting the same result there's not a problem with that. That doesn't mean it's broken, okay? So these are just kind of some, hopefully this should look familiar from our first unit about functions, okay? Now, a one-to-one function just makes, it's one-to-one. Each X value only has one Y value, and so on. So that's kind of where I put, each partner is going to be faithful in a one-to-one function. Okay. So back to inverse function. So the only way you can have an inverse function is if it is one-to-one. Because if you look at this example right here, if you were to switch this, if you were to put it as 8 and 2 and maps into -2, 2, 1, then 8 would be pairing up with two different partners, and now your X value's got two different partners, and that would be a problem. This would not have an inverse. This does not have an inverse function. This mapping right here would not qualify of having an inverse function, because if you switch roles, all of a sudden you have the problem we have over here. All of a sudden you have this problem, okay? All right. So you can also use the graph of a function to determine whether it is one-to-one, and that's what we're mostly going to focus on. So this should actually be pretty simple. Explaining it with mappings can definitely be a little challenging, but looking at graphs, this is pretty simple. Kind of like the vertical line test, instead we're going to do a horizontal line test, okay? So similar to the vertical line, if you drag a horizontal line down the graph and the function and it touches the graph at no more than 1 point at a time, then the function is one-to-one and has an inverse. Okay, so first of all, let's get this out of the way. These are all functions. These right here are all functions, and I'll show you real quick. Like I said, this should be a review from our very first unit. So see, it only touches at 1, touches at 1, touches at 1. So all those, they pass the vertical line test. And so that was given, by the way. It's given that they're all functions. But now we're going to use the horizontal line test to figure out if they are one-to-one. And so it has to pass the test horizontally where it only touches at 1 point. So this one looks good. This one, not so much. This one has a problem. Okay. Same thing with C. That one has a problem. Let's see. Part D looks good. Part D looks fine. Part D looks good. Okay, so let me go ahead and mark those, and then I just want to talk about one other thing. So this one is a function. Yes, no, no, and yes. Okay, so parabolas on their face don't have inverse functions, but what we can do, and we'll see this, and you might see this on some examples in your homework, they might do something like this. They might say, well, what if we say X can only be greater than or equal to 0? And so what that does is it cuts off this part of it. It cuts off this half of it, because you're only considering the positive X values, only the X values that are greater than or equal to 0. So now all of a sudden this one is actually one-to-one, and it does have an inverse function. So just be aware sometimes, and you might see this on your homework, I think we'll see this in one of our examples, that sometimes we'll use this notation to where that will allow one that typically would not have an inverse function, but you can adjust your X values to where it will have one. Okay, so that'll be part 1 of inverse functions. So the next video will discuss how to find the inverse of a function if you're given one, okay?